All right, let's get right into it. Today, we're going to crack a code, but not some kind of military secret or a message from aliens. Nope, we're talking about a code that's hiding in plain sight, inside every single word you use, every single day. It's the hidden mathematical structure of the English language.
So take a look at this. It seems like complete nonsense, right? Rod, not, one, SMOL. This totally cryptic message comes from a real experiment back in 1951, run by the legendary engineer Claude Shannon. See, the original sentence was just normal English, but after being passed through a special process, this is what came out.
And here is the central mystery for today. Believe it or not, that bizarre stripped-down text you just saw contains the exact same amount of information as the original sentence. Not a single bit was lost. How on earth is that possible? Well, to figure that out, we have to ask a much bigger question.
And that question is, what even is information? This is what Claude Shannon was determined to figure out. You have to think of him less like an engineer and more like a detective. And the concept he was hunting was information itself. He needed a way to actually measure it.
The key idea he landed on was something called entropy. Now, don't let that word scare you off. In this context, all it really means is surprise. Shannon's big insight was that real information is the part of a message you can't predict. It's a measure of randomness. So the less predictable something is, the more surprise and the more information it carries.
Let's make this super clear with a quick comparison. On the left, you've got a total jumble of random letters. Every single letter is a complete surprise, right? You've no idea what's coming next. That's high entropy, which means high information. But on the right, look at the phrase, see you later. Once you see the first few letters, see, you, lay, you're not at all surprised when a T shows up. It's predictable. That's low entropy, and therefore low information.
So, armed with this powerful idea of information as surprise, Shannon started to hunt for patterns in English. He wanted to measure its true information content. And he started out like any good codebreaker would, by looking for statistical clues. His first method involved something called n-grams. It sounds a little technical, but I promise it's really straightforward. You just look at the frequency of patterns. First, you analyze single letters, then you look at pairs of letters, then triplets, and you just keep going, seeing how predictable the patterns get. Okay, so let's set a baseline. If every letter of the alphabet was completely random, if each one had an equal chance of appearing, the entropy of English would be 4.7 bits per letter. You can just think of a bit as a single unit of surprise. But of course, we all know that's not how English works. Some letters are way more common than others. E is everywhere, Z is pretty rare. The moment you account for just that simple fact, the frequency of single letters, the entropy immediately drops to 4.14 bits. The amount of surprise is already going down. Now, let's take it one step further. What about pairs of letters? You know that if you see a Q, a U is almost certainly coming next. T and H are constantly together, but a Q followed by a Z? That's basically impossible. When you factor in the predictability of these pairs, the entropy drops again, all the way down to 3.56 bits.
And Shannon himself put it best. He said that as you look at bigger and bigger chunks of text, 3 letters, 4 letters, whole words, you're including more and more context. And the more context you have, the more predictable the language gets, and the closer you get to its real core information content. But pretty soon, the statistical tables just weren't big enough.
And this is where Shannon had an absolute stroke of genius. He realized that trying to calculate this stuff with brute force could only get him so far. He needed a much more powerful pattern recognition machine, and he realized he had access to one, the human brain.
Shannon's huge insight was that every single one of us, just by speaking and reading English our whole lives, has become an incredible prediction engine. We have this deep, intuitive grasp of the language's patterns that no computer back in the 1950s could even dream of matching.
So to tap into that power, he designed this beautifully simple experiment. It's basically a guessing game. He'd sit someone down, show them a bit of text, and just ask them to guess the very next letter. If they got it right, great. If they were wrong, he'd tell them the correct letter, and then they'd just move on to the next one. That's it.
Now here's the crucial part. Shannon proved that this whole process was perfectly reversible. So think about it like this. Imagine the person playing the game has an identical twin. If you took that twin and you only gave them the list of letters their sibling guessed wrong, they could reconstruct the original text perfectly. Why? Because they'd make all the same correct guesses on their own, and you'd be filling in the blanks for the exact same mistakes. Absolutely zero information was lost.
And when Shannon took a look at the data from this guessing game, well, the results revealed something absolutely stunning about the nature of the English language itself.
The results were just incredible. With zero context, just guessing the first letter of a text cold, people were right about 18% of the time. But give them just 5 letters of context, and their accuracy skyrockets to 58%. And with 100 letters of context, they could predict the next letter correctly an amazing 80% of the time.
And get this, across a typical experiment, Shannon found that his subjects guessed the right letter on their very first try 69% of the time. Let that sink in. Nearly 7 out of every 10 letters in any normal English text are so predictable that we can guess them correctly with no hints at all.
And that solves the mystery from the very beginning. Remember, information is surprise. All those letters people guessed correctly, that huge 69%, they weren't a surprise. They were predictable, which means they carried almost no new information. And that is why you can get rid of them and create that weird-looking text without losing anything important.
So Shannon's final conclusion was a landmark discovery. The true information content of English is way, way lower than anyone thought. He found that our language is about 50% redundant. About half of everything we write is kind of predetermined by the rules and patterns of the language itself. And this isn't a flaw, it's a feature. It's what makes our communication so robust. So, a fascinating 70-year-old paper. Why does any of this matter to you today? Well, it's because its discovery, this idea of measuring and using predictability, is the foundation of the digital world we all live in right now.
I mean, seriously, it's everywhere. Every time you zip a file or save a JPEG, you're using an algorithm to find and remove redundancy, just like Shannon did. That predictive keyboard on your phone? It is literally playing Shannon's guessing game with every word you type. The error correction that keeps your Wi-Fi from dropping, and even the gigantic large language models that power modern AI, they all stand on the shoulders of this one idea: understanding and exploiting the hidden patterns in data.
And that really leaves you with a final thought, doesn't it? Shannon pulled back the curtain on this deep, invisible mathematical structure, hiding inside something we use every day without a second thought. It just makes you wonder, what other invisible patterns, what other hidden codes are shaping our world right now?